Hello everybody. Today I'll be talking to you about a common purification method used in organic chemistry called recrystallization. So, what is recrystallization? Like I mentioned in the title slide, recrystallization is just one way chemists have to purify compounds, and specifically recrystallization is a method used to purify solid organic compounds. As an example, a way to purify liquid compounds would be something like distillation. Now, there are many ways recrystallization can be done to be successful and produce a highly pure product. And today we'll be talking about just two of those methods. So single solvent recrystallization and mixed solvent recrystallization. And we'll get more into depth in that later on. And this video on the right is just one example of a compound being crystallized from a solution. So why would a chemist want to use recrystallization over other methods? Compared to some other common methods of purification, recrystallization can be faster, it can be less wasteful, it can be greener, and some characterization methods that chemists use, such as X-ray diffraction, require highly pure single crystals that can only come from complicated recrystallization techniques. Also, it's really just neat to watch. So, how does recrystallization work? Recrystallization takes advantage of the dependence of solubility on temperature. So when you increase the temperature of a solvent, the solubility of organic compounds within that solvent is increased. And so you can make a saturated solution at an elevated temperature, which then becomes a supersaturated temperature once it's cooled. And then once it's disturbed, the compounds of viscérants will come out of solution because it's no longer soluble in the solvent. And this graph we have here shows the solubility curve of sucrose, or table sugar, in water. And as you can see, as we approach the boiling point of water, the amount of sucrose that can dissolve in water almost doubles. This lets us take advantage of the fact that we can use minimal amounts of our hot solvent to dissolve our compound that isn't soluble at room temperature, and then allow it to slowly come out of solution while it cools back down to produce highly pure crystals. Now that we have a mixture of compounds we want to purify, we have to figure out how to remove impurities to get a single pure solid. And in the recrystallization, filtration is how we do that. Now there are two methods for filtration that will be used in the recrystallization, either gravity filtration or vacuum filtration. Gravity filtration is used to remove solid impurities from a liquid solution, if present, and like it states in the name, it uses gravity to drive the separation. This filtration can either be done as a hot filtration or a cold filtration. A hot filtration will be done to remove solid impurities during the recrystallization process that aren't soluble at all in the solvent, or as a cold filtration to remove solid impurities such as drying agents when not doing a recrystallization. The picture on the right shows a generic gravity filtration setup. A glass funnel is suspended above a flask with a piece of filter paper placed inside. The hot solvent with insoluble impurities is then poured into the filter, and the hot solvent drips through, leaving the solid impurities behind. Now, you can kind of think of gravity filtration as similar to making a pot of coffee. There's a physical setup with a glass funnel suspended above the collection flask with a piece of filter paper inside. And this is similar to a coffee pot, which has the coffee maker, the coffee pot that will eventually hold your freshly brewed coffee, and the coffee filter to separate the coffee beans from the freshly brewed coffee. We use this piece of filter paper in the gravity filtration to separate the solvent from impurities that we don't want, just like how coffee pots use their coffee filters to prevent the ground coffee beans from getting into your coffee. The other filtration method is vacuum filtration. It's often used to remove liquids from a solid product and then as a way to dry the solid product. Vacuum filtration can also be used to remove solids from a liquid if the liquid is of a large enough volume, because gravity filtration can be quite a bit slower. Vacuum filtration uses a pressure differential as the driving force for the separation. This pressure differential, or vacuum, can either be from a water aspirator, which uses water flow to create a vacuum in the collection flask, or a vacuum pump to create a vacuum in the collection flask. Vacuum filtration is usually done as the last step of recrystallization before taking melting points as a way to dry the crystals. You wouldn't want to use a vacuum filtration as a hot filtration step because when you apply a vacuum to the solvent, the boiling point of the solvent will decrease. So if you were to do a hot filtration via vacuum filtration, your solvent would likely boil away to the extent you would get premature crystallization and you'd have to start all over. The picture on the right shows a generic vacuum filtration setup. We have a heavy glass-walled vacuum flask which will be connected to the vacuum and a Buchner funnel placed inside of a rubber adapter that seals the flask. The vacuum is applied, pulling liquids and air from outside into the flask quickly. This removes the solvent from the crystals and also dries the crystals as air is constantly flowing through them. As you can see, there are many steps in the recrystallization process. Step 1 is to choose your recrystallization solvent. Step 2 is to add the hot solvent until your compound is fully dissolved. Step 3 is to remove any remaining impurities that are present in the solution. Step 4 is to cool the solution to room temperature. Step 5 is to induce crystallization, if it's necessary. Sometimes it will be and sometimes it won't be. Step 6 is to perform a melting point analysis to compare your crystals to known literature values if it's a known compound. And then step 7 is to repeat steps 2 through 6 if the crystals are not as pure as necessary. Going a little bit more into detail, starting with step 1, choosing the recrystallization solvent. This is perhaps the most important step in the process. A good solvent for recrystallization will do the following. It will dissolve very little or none of the compound at room temperature. It will dissolve all the compound at an elevated temperature. It'll have a boiling point between 60 and 100 degrees Celsius. It'll have a low vapor pressure, so it'll be easy to remove. It won't be overly hazardous to work with, and it shouldn't react with the compound in any way. The Lab Companion has a great list of recrystallization solvents with boiling points, melting points, and comments about the properties of each of those solvents in regards to recrystallization on page 177. Moving on to steps 2 and 3, dissolving the crude product and removing impurities. To dissolve the crude product, you want to add minimal amounts of the hot solvent in portions. If you add too much solvent, the compound may remain in solution even while cold, and you'll have to start the process over after removing the solvent. If not enough is added, the compound won't fully go into solution. We're trying to balance the saturation of the compound in the solvent. You want the solution to just barely be saturated in the hot solvent, so that it'll come out of the supersaturated solution once cold. Now, to remove impurities, there are a lot of ways depending on how the impurities are present. If solid impurities are present, you can perform a hot filtration by adding an excess of hot solvent to prevent the compound from coming out of solution, and then filtering through filter paper quickly via gravity filtration and allowing the excess solvent to boil away after collecting the filtrate. If colored impurities are present, a small amount of activated carbon can be added to the boiling solvent and allowed to stir for a short while, along with adding a bit more hot solvent to prevent recrystallization from occurring and performing a hot filtration like earlier. If dissolved impurities are present in the hot solvent but insoluble in the cold solvent, I'm sorry, but you're going to have to start over with a new recrystallization solvent, as both compounds are now solid again and mixed together. If dissolved impurities are present in the hot solvent and soluble in the cold solvent, they will remain in solution and can be removed via filtration and discarding the filtrate. Steps 4 and 5, inducing crystallization. First, you want to allow the solution to cool slowly to room temperature, as this will give better crystals. Once allowed to cool to room temperature and if no crystals are present, there are a few things that can be done to induce crystallization. You can cool the solution further in an ice water bath to lower solubility further. You can introduce a glass stir rod and scratch the bottom of the flask to disturb the solution to cause crystallization, or you can introduce a seed crystal into the solution. Typically, what you will do is a combination of 1 and 2, so a combination of cooling the solution in an ice water bath and introducing a glass stir rod to disturb the solution. Step 6. Melting point analysis. Melting points can be used as a spot check for purity after recrystallization. If impurities are present in a solid, they will broaden the melting point range and also decrease the melting point range. And so as recrystallization removes impurities, the melting point range can be checked and compared to known literature values. If the values received are close to literature values, we can stop here and observe the crystal's appearance and get additional characterization data. Or if the values received are not close to literature values, subsequent recrystallizations can be done to further improve purity, as we'll see in the next slide. And this picture on the right is a reminder of how to correctly choose initial melting points and final melting points for determination of melting point ranges. So that way you can be as accurate as possible during these initial determinations for purity. This leads into step 7, repeat if it's necessary. Now we have to start the process all over again. So I'm going to start all the way back at the beginning, and we're going to go with dissolving the crude product and removing the impurities. And just kidding, we're actually going to move on to our other method of recrystallization today, mixed solvent recrystallization. And so you may be wondering how to choose between a single solvent recrystallization and multi-solvent recrystallization. And it's pretty simple. If the crude product can't be successfully recrystallized from a single solvent, it's time to move on to a mixed solvent recrystallization. As you can see, the steps in a mixed solvent recrystallization are very similar to a single solvent recrystallization. We still remove impurities, induce crystallization, and perform melting point analysis in the same ways as a single solvent recrystallization. The major differences in a mixed solvent recrystallization are how the solvents are chosen and how the solvents are added, and that's what we'll be going over in the next couple slides. For a mixed solvent recrystallization, the solvent system should have one solvent the compound is completely soluble in, have one solvent the compound is completely insoluble in, and the two solvents should be miscible with one another. Now, miscibility is a property of two substances that form homogeneous mixtures in any concentrations. The chart on the right is an example of the solvent miscibility table, where you can see if certain solvents are miscible or immiscible with one another. This is a nice chart to reference when looking at a mixed solvent recrystallization, especially if it's going to include water. Properties of a solution of miscible solvents can change with temperature. For example, a solution of ethanol in water at high temps will behave as an alcohol, and at low temperatures will behave as water. So now on to steps 2 through 4, dissolving crude product and removing impurities in a mixed solvent recrystallization. The first part is to dissolve the crude product in a minimal amount of your hot solvent A. And if any solid impurities are present at this point, this is where they would be removed via hot filtration. After the solution has gone clear, you will then add small amounts of hot solvent B until the solution is cloudy. What this is doing is it's slowly reducing the solubility of our product in the mixture of the two solvents until it's no longer soluble in the mixture. After the solution is cloudy, add hot solvent A dropwise until the solution is clear. This is very slowly increasing the solubility of our product to the threshold of being a saturated solution of the mixture of solvents while it's hot. And then once that's done, you would remove impurities in the same methods as before. And then we move on to inducing crystallization, and the process is identical to that of a single solvent recrystallization. And with that, that's the end of the presentation. Thank you for watching, and if you have any questions, don't hesitate to reach out.